So we've assumed that intrinsic regulation of GFR is not sufficient. So the kidney is calling in the central nervous system and endocrine systems to control GFR via extrinsic, so central control. So our stimulus is still a drop in systemic blood pressure, and that's going to do a couple of things in addition to this local regulation. One is baroreceptors. So baroreceptors detect this at the aortic arch and carotid artery, and they are going to decrease in their firing. This is going to trigger the sympathetic nervous system. The sympathetic nervous system is going to do various things, including vasoconstriction of all the systemic arterioles. What does this do? This acts to increase blood pressure. This piece over here is a nervous system response, right? Add that here. Nervous system. That probably tells us we're going to have endocrine system over here, a hormonal response. And I'll just give you a teaser, even though we're about to do it. RAS. Okay, renin, angiotensin, aldosterone. You don't know, however, how this gets triggered. We actually didn't talk about this. We knew renin release occurred, right? So renin release, we've got to have that. Renin is going to be released from our granular cells, which are in that afferent arteriole that goes to the kidney, to the glomerulus. These granular cells can be triggered directly by low blood pressure. They detect blood pressure because they're in that afferent arteriole. They also can be triggered by the sympathetic nervous system. Okay, renin is going to activate angiotensin. So angiotensin 2 will be formed. That's going to have various effects that you should be able to list. There's going to be 4 responses, I'll show you in the next slide, that all are going to act to increase blood pressure. One is through vasoconstriction. All right. The one other thing, since I have 2 things listed here, the stimuli for those granular cells, one is they have stretch receptors I told you about before. They can be stimulated by the sympathetic nervous system. They also can be stimulated by ATP. What releases that? Our macula densa cells. So intrinsic regulation, that intrinsic response can also trigger this long-term response. And this long-term response takes longer then. Okay, angiotensin. Let's remind ourselves what that does with a picture that I did not draw. Isn't it nice? So this is a response, a long-term blood pressure response. How do we know that? Because we're altering blood volume, right? And we saw this response with blood pressure regulation in our blood vessel and pressure chapter. So nothing new here besides, even from chapter, whatever it was, besides now we know the granular cells are what's releasing renin to produce ultimately angiotensin 2. ACE from the lungs is also involved in that. Remember we talked about what ACE inhibitors would do to blood pressure. So to remind you, the results of angiotensin 2, which is a learning outcome from your previous unit that you should still know, One, ADH release. ADH is going to cause water reabsorption by the kidneys. We'll see where this happens. It's going to be the collecting duct. So we'll look at that more closely. We have the hypothalamus triggering thirst via angiotensin stimulation. We have vasoconstriction. This one is short term. It happens quickest because it's not a change in blood volume. And we've got aldosterone that's also secreted by the adrenal cortex on top of the kidney. Aldosterone is a hormone that's going to result in sodium and water retention. This is going to be in our primarily the distal convoluted tubule. So we'll see that. So kidney, right, highly involved in this long-term regulation, both in terms of initiating the stimulus here, one of the initiators. Well, it is the initiator for this RAS pathway, and also response in terms of water retention.